All right, so we did talk about securing the hardware of our devices. We talked about securing the network protocols that make our networks actually work. We talked about securing the application protocols that transport the application data that we all want to send over the network. But there's one more piece of the puzzle here. That's the application itself, right? That the application code. How was that code designed from the very beginning in order to ensure at least some level of security? Because whenever an attack happens, whenever a data breach happens, whenever you hear about an exploit in the media, or any type of attack basically, there's going to be some sort of vulnerability that was exploited. And that vulnerability is more often than not a vulnerability built into an application. Sometimes it's a vulnerability in the protocol itself. That doesn't really happen that often, even though it's pretty dangerous when it does. But most vulnerabilities out there relate to a specific version or a specific release of an operating system or of an application that is running on top of that operating system. And that's the root of all evil. That's where all the vulnerabilities stem from, and that's the target of pretty much all the attacks out there. So let's talk about application attacks and see how we can protect those applications, starting from the actual design of those applications. And by the way, this is one of my favorite topics in CurityPlus. And besides the fact that it's one of my favorite, unfortunately, it's also one of the more complicated ones, because it does require you to have at least a bit of understanding about what's going on within the software development process, and also to understand a bit about what's going on inside of an operating system, how operating systems work and how memory is managed and stuff like that. So we're going to dig into a couple of more, let's say, in-depth discussions in here, but fortunately the CurityPlus exam doesn't really ask you to know that much, go that deep into these topics, because we could be building an entire training series just talking about securing application code and writing secure applications. We're not going to do this right here, but we are going to present a brief overview of pretty much the bare minimum that you need to know for the exam and for your general knowledge. So when you read in the media or on social media or whatever media you're reading about attacks that, company X has been breached, or the product of a certain company was hacked, or their application was hacked, or their computer was hacked, or somebody was hacked, what exactly does this mean? Well, the end result is the one that we can easily understand, right? The end result, the action on objectives of an attack is usually to steal some data, to gain access to privileged information, to perhaps destroy some sort of data, or to cause a denial of service. But how exactly does this happen? I mean, applications are not designed to be hacked, obviously, right? So what exactly is a hacking process? Just to start with a brief definition here, and this is one of those things that many people don't know about. The definition of hacking from its beginnings actually meant using a system or using some sort of a device or a service in other ways than it was initially designed for, than it was intended to be used. So whenever you're trying to brute force a password, or you're trying to break an authentication portal, or you're trying to exploit a vulnerability in an application, well, you are then using that service or that application in some other way than it was designed. That is hacking, and that's a hacker basically. It's a person who attempts to use a system in other ways other than the ones it was designed for. So that's hacking from a historical perspective. So you can probably guess that initially hacking wasn't really attached to a negative connotation. So it did not have this negative meaning that it currently has of malicious intent. Well, nowadays it kind of does. And we all know that we don't want to be hacked. We don't want to face a hacker. We don't want to be facing an attack coming from the outside or from the inside. But the root definition still stands. And at its core, hacking means exploiting a vulnerability. Now, a vulnerability is a flaw in the design of the software. It's a flaw that allows that software to be used in some other way other than it was designed for, right? Just the definition that we just talked about. And since the definition of security, like we learned from the very beginning, was to protect the confidentiality, the integrity, and the availability of our systems, well, guess what? Hacking aims at attacking or destroying exactly these three pillars. So we're either attacking a system to break confidentiality, to gain access to privileged information, to destroy integrity, that is to maliciously alter some information or simply destroy that information altogether, or to deny access to a service, and that is going to be a denial of service, right? This is what breaks availability. So the end game of a hack kind of matches the actual pillars of security, attacking either C or I or A. And how exactly is this being conducted? Well, exploiting a vulnerability, in many cases, it means that the attacker is somehow succeeding in executing arbitrary code. Now, what do we mean by that and why is this important? Well, when you are legitimately using an application, it might be a web app, it might be an app on your phone, it might be an app on your desktop, you're basically executing the application's code, right? You are executing instructions within that application the way they were designed to be executed. Well, hacking an application or exploiting a vulnerability means that you as an attacker somehow managed to trick that application into executing a piece of code that doesn't belong to it, but it belongs to you. So you're basically making that application do something that it wasn't designed to do because it starts executing some foreign code. And with that foreign code, you can basically make that application do whatever you want. Don't forget that it's not the actual application itself that is executing that code, but it's the operating system that is hosting that application that it's executing your arbitrary code. So at the end of the day, if you think about it, whenever you trick an application into executing some foreign code, you're actually tricking the machine that is running that application on into executing your code. And guess what? If you manage to trick that machine into running your own code, it might be running with the same privilege as the hacked application. Or if you're really smart about it, you can even trick the machine into running that code with root privileges. And there you go. You have owned that machine. You can make it do whatever you want. You can now use it to launch a secondary attack. You can now use it to access any kind of data, any privileged data that might have been hidden from you as a legitimate user. You can basically do pretty much anything. So it all boils down to code execution. And we have two terms for this. We can call it arbitrary code execution. That is when the attacker injects its own code into the application and tricks the application into executing it. Or remote code execution, which is pretty much the same thing, except that we are now focusing on the fact that the code is being sent from over the network, so even from outside, right? Perhaps even over the internet. So it's a kind of exploit that is conducted from a distance, hence the word remote. Application privileges are relevant because we just said that whenever you're hacking an application, you're basically tricking that application into executing your own code. But that code gets executed with the same level of privileges like the application that you just hacked. Now, those applications, depending on where they are, what types of applications they might be, let's say that it's a web server that is hosting a web application, that it has some vulnerabilities in it, and you can trick that web server into executing your own code. Now, that web server might be running with a dedicated user. It might be running with a more privileged user because, well, somebody thought that they don't really want all the hassle of managing permissions, and why not give the web server permissions everywhere to do whatever it wants? And that's a bad thing because you didn't apply the principle of least privilege. And this becomes really useful, especially when that application is hacked. Because if the application is running with root or admin privileges on your machine, then whenever a hacker manages to take control of it, they can basically take control over the entire machine because they already can execute code with root privileges. Also, I have to keep in mind that there has to be some sort of a balance between security and permissions, because an application, in order to work, it's still going to need access to the network. It's going to need access to the disk. It's going to need access to perhaps one or more databases. It's going to be able to call some remote APIs, perhaps. So it does need a certain level of privileges. You cannot just, cut all connections to the outside, because otherwise the application becomes completely useless. So you have to find the exact balance between the right amount of privileges required for your application to work and to make sure that those privileges are not too high in case that application gets hacked. And since we don't really have any rules in this realm of hacking, You can probably guess that, well, a hacker might not be content just to execute the code that it's injecting using the application's privileges. This is why a concept known as privilege escalation has been discovered in a lot of attacks. And we actually have two types of privilege escalation. We can have vertical privilege escalation, where an attacker first exploits a vulnerability that allows it to execute code with a regular user or with the regular user that is being used by the application that just got hacked. And then by exploiting an additional vulnerability, perhaps in the operating system, perhaps in another service on that system, it gains access to a higher set of privileges. It can suddenly start executing code with a root privilege level, with an admin privilege level, something higher than the set of privileges of the application that was initially exploited. So that's vertical PE, privilege escalation. Horizontal privilege escalation means jumping the fence into the privileges of another user, perhaps on the same level. So you might be able to hack a user's account, but that might be just a regular user, right? You're not interested in the data that that user has access to, but you can use it. You can use that user account to further exploit another account on the same machine, perhaps, or on the same network in order to gain access to different data sets. So if you manage to exploit a regular employee's user, you might be interested in reading the CEO's email, right? So that would be a horizontal privilege escalation, right? Jumping from one user account to another. How do you detect this? Well, it can be detected because it generates a bunch of events. Now, pretty much everything that happens on a system, and ideally everything that happens on all the systems, should be gathered in some centralized location such as a SIEM. You should be able to see just by looking at the audit logs, just by looking at the event logs that get generated, the fact that a user has escalated their privileges. Whenever you see a regular user in a log message performing an operation that the user should not normally be allowed to perform, well, that's going to be a huge red flag. But of course, you need monitoring for this, and you need correlation for this as well, because disparate events, if not correlated with some more information, such as, has this user ever performed this operation in the past? Or does this user belong to a group that normally does this type of operation? If you don't have this intelligence, this information available to you, then you're not going to be able to detect these privilege escalation attempts, and they will go unnoticed. Application errors will happen, so we're not here talking about how to avoid these errors from happening altogether, but how do we handle those when they happen. Now, during the software development of a software product, it is expected to generate as much information in your errors in order to help with debugging and help with troubleshooting. Whenever something bad happens, especially if the software is in test, maybe it's in user acceptance testing, maybe it's tested by a limited set of users, it's useful to get as much info about an error condition as possible, because then you can see exactly what happened in there. Oh, so this was the error, this was the process that caused it, this was the line in the code where the error happened. Go ahead and fix it. But when you're shipping that product in production to the end customer, and when that product becomes live and exposed to the outside world and to potential attackers, those verbose error messages should not be there anymore, because the more information you give whenever an error occurs, the more information an attacker can gain just by observing the way your software works. So it's much better to have some simple errors, such as a general exception, unhandled exception, error code something. Don't dump the entire stack trace. Don't offer the entire SQL query that failed. Don't offer details, inner details about what function calls were performed before the error happened, what type of files were open, which location on the disk returned an error due to insufficient permissions. Whatever caused that error, don't give this information to a potential attacker. Now, if you want to keep a separate version of that application with more verbose logging for internal testing and debugging and troubleshooting, feel free to do so, but don't give a potential attacker more information about your application, because you're making their job easier. You're basically helping them understand your application and understand how it could potentially be hacked. A very basic example of this would be a simple username and password validation. Right? You have a login portal with a username and a password field. If you enter the right username but the wrong password, you might be tempted to provide an error message saying bad password for user XYZ. Don't do that, because that's already an indication for a potential attacker that the username is a valid user. So they can continue trying to break that user's password because they now know they have encountered a valid username. Just give a generic error message, failed login, right? Wrong credentials. You don't really have to tell it whether it's the wrong username or the wrong password. Just fail the authentication altogether and let the legitimate user figure out what they need to do in order to log in. Don't give more information than necessary to a potential attacker. And remember when we said that basically hacking an application means tricking that application into executing somebody else's code? Well, this requires input to the application, right? An attacker has to be able to somehow send some sort of data to the application, and then they need to start thinking about how to trick that application into executing what we just sent. This something that gets sent to an application is called input. And pretty much every application out there accepts some sort of input. I mean, every web application accepts input, at least for the potential URLs that you can send to it and the resources that you are able to request. Some web applications allow you to upload data, upload files, upload profile pictures, post comments on a forum, for example. That's also input. All the applications on your desktop, on your laptop, they also accept input. On your mobile phone, the simple fact that you're interacting with an interface, that you're clicking around, that you're using the keyboard, that you're tapping on the screen, or you're dictating something to an application, this becomes input. And unfortunately, this is the root of all evil. Input validation, or unvalidated input, that is the #1 cause of pretty much all the software flaws out there. Because whenever an application gets hacked, gets breached, 99% of the time, it's going to be a type of input that the application designer did not think about, did not think that it would happen, and when it happened, it was able to exploit the vulnerability. So, unvalidated input. So #1 rule here, validate all the input that you are receiving from your users before you're actually sending it to be executed by the application. A successful and 100% input validation process would probably make this entire training and all the cybersecurity business all over the world completely obsolete, because there would be nothing to protect against. If you don't validate your input, then you are opening up yourself to a whole bunch of risks and potential attacks out there. So, how do we validate input? Well, you could do it on the client side, or you could do it on the server side. Which one do you think is better? Well, actually, a combination of both. If you think about it first, if you just try to keep things simple here, if you validate the input on the client side, that is going to be easily bypassed. Because if you have a web page, let's say, and you're trying to mitigate against, let's say, SQL injection attacks, right? And you don't want to accept anything that looks like an SQL statement in a username field, let's say. Well, if you do this validation on the browser side, like in the JavaScript of the web page that gets executed by your browser, a potential attacker, of course, could easily circumvent that JavaScript code because they have access to the actual web page code, and they can easily modify it and say, just ignore this piece of code and just send whatever I want you to send. So this can be easily bypassed. On the other hand, validation on the server side is much more efficient because now the attacker or the user doesn't have anything to say about the result of that validation. You're simply sending all your valid data or your injection data, whatever you're sending, and then the server side is going to accept or reject what you just sent based on the configured security policies. A combination of both could be beneficial in situations where you're not trying to protect against malicious users, but against normal user errors. So for example, you could have a small piece of JavaScript code telling you on the client side that username should only contain letters and numbers. And if you accidentally type a hyphen in there or a dot, it's going to immediately make that field red and tell you that the only accepted characters are these, this, and this. All right. That's also a type of input validation, but it doesn't protect you against attacks. It's simply a type of input validation that helps your legitimate users understand the way that application is supposed to be used. On the other hand, of course, the real input validation should happen on the server side. So don't just assume that because of that small piece of JavaScript code that doesn't allow your username to contain anything else than letters and numbers, that nothing else other than letters and numbers are going to reach your web server. No, don't assume that, because again, JavaScript can be circumvented, can be bypassed. So on the server side, make sure that you thoroughly check the entire data set that you're receiving from your users on every possible input scenario. Check the web form inputs, check the input that's coming in from the network as network data, check the binary data that's coming in, check the length of the data that is coming in, check the structure of it, and make sure that you don't allow your application to process data sets that it wasn't designed for. Checking the length of the data is useful because there are attacks that are based on buffer overflows. Now, a buffer is just a memory area that was pre-allocated by the application in order to store whatever is coming in from the user. Now, if the user is trying to send more data than the buffer can hold, a buffer overflow is going to happen. And the way computers are designed is that whenever they start writing from a specific address in memory, they're not going to stop when the space runs out. No, they're going to keep going and overwrite whatever comes after that pre-allocated space, which might be application code, which might be other buffers, which might be input coming in from other legitimate users, and so on. So that's buffer overflow, right? A code injection can happen due to input validation as well. If you don't validate whatever your users are sending you, you might end up seeing that instead of a legitimate username, you just received a script. A bash script that gets executed by the web server, or a JavaScript that becomes part of the comment or the forum posting that the user has just submitted. And that JavaScript code is now displayed and executed by whoever else comes in and displays the same comment on the same web page, right? That's cross-site scripting, for example. Other errors can also be caused as well, right? Could also send an input with the simple purpose of crashing an application and causing a denial of service. So as we said before, a buffer is just a pre-allocated memory space in order to prepare that space to store whatever comes in from the user, in order to, of course, later on process that data. Now that buffer, of course, has to be limited, because nothing is unlimited in this world. So you prepare a buffer, you allocate some memory from it, and you expect then input data coming in from the user to be stored in that buffer. Now the problem here with overflows is what happens when the user sends more data than the buffer can store. Normally, your application should check for this and reject that type of input, but if it doesn't reject it, we can run into an attack that is called a stack overflow. Now, to better understand how a stack overflow happens, let's have a quick detour into understanding how a program memory looks like whenever it's running in your computer, whenever you've launched already an application and it's currently running in the memory. That's what the program sees as far as the available memory. So first of all, we see a memory structure here starting from the lower value of 0 to a higher value of whatever or how much free memory you currently have on your system. This is virtual memory, by the way. So theoretically, your program is going to see more memory than you actually have free on your system. Now, it also divides the available memory into a couple of segments here, starting with the text segment. This is where the actual application code is stored. So this is where your code, your instructions are going to be stored. Then comes the data segment. This is where your variables are going to be stored. Then we have the heap right here. This is where the, I like to call it the big stuff is stored. That is files loaded from the disk, input coming in from the network, images, media files, whatever your application needs to use. That's the heap. At the top here, we also have the kernel, or part of the kernel. As far as the application is concerned, this is the area where the parameters, the environment variables are accessible. And right beneath this kernel, we have our stack. Now, the stack here is a bit of a special memory area from two perspectives. First of all, the stack is used whenever your normal program code jumps into a sub-function or another procedure inside of its code. So starting with the main function, for example, in C or C++, and then jumping into another function, that's when the stack is going to start to be used. And what happens with the stack here is that whenever the main program execution jumps inside of a different function, the stack is being used to store a number of things. First of all, it's going to store the return address for the code. because once the code execution jumps inside of a different function, and then that function ends, you reach the end of the last instruction in that function, you need to come back to jump to where you were before calling that external function in order to continue execution. So this return address right here is going to be really useful, because otherwise you're going to break your program's execution, right? So return address tells your program where to go after the function execution has finished. Another thing that gets stored on the stack is the actual function arguments that the function you just called received as part of its call. So you might have some sort of a input processing function that says process user data, or process user input, or process login credentials. Well, that function is going to receive the actual input data, the actual login credentials, right, in order to validate those. Well, those arguments are going to be stored right here on the stack. And as many of those arguments we have, they're going to be pre-allocated here as part of some buffers. So this is where the problems start. Notice that the entire memory area that we see here on the slide starts from 0 up to a higher value. So basically it grows up, okay? But also notice that the stack right here has a down-facing arrow. So as weird as this might sound, the stack actually grows down. So it grows from higher memory values to lower memory values. If I have multiple functions in here, they're going to end up one after another. So I might be calling a function that calls another function, that calls another function, and calls another function. And there you go. I keep going deeper and deeper in this stack. But it's not a stack like a stack of plates that grows upwards. It kind of grows downwards. That's how it was designed. Now, the problem with this approach is that even though the stack grows downwards, whatever memory addresses or whatever buffers are being allocated within this stack are still going to be allocated. So for example, this buffer of 10 elements right here is still going to be allocated from lower values to higher values. So what happens here is that we are allocating the buffer from high to low, but we're starting to write in that buffer from low to high. So basically we are writing it from the bottom to the top. Notice a potential problem with this. Well, this buffer here of 10 characters, let's assume that this is the buffer that receives a username from me, right? That's the web application here that expects me to provide a user. And let's say that I am willing to provide a user here that says Andrew. There you go. Now, this Andrew right here is going to end up in this buffer, but it's going to start being written from low values to high values. So from the bottom to the top or from the right to the left. So it's going to be something like this. A-N-D-R-E-W. Now that was weird. Okay, so this is how it's going to be stored. As long as this input here, which is 6 characters, can be held within this buffer here, everything is okay. I could even go higher and say Andrew 1, 2, 3, 4. All right, then would be I had a 1 and a 2 and a 3 and a 4 in here, and there goes my entire buffer. Now, what's going to happen now if I keep sending a longer and longer input? Instead of Andrew 1, 2, 3, 4, let's say I'm going to send it Andrew 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. What's going to happen with this is assuming that my program doesn't validate the input that I'm sending here. So it's not going to be 6 characters anymore. It's going to be a lot more. So I'm still going to be writing this entire data set starting from the right here. Going to go through Andrew 1, 2, 3, 4. And I'm going to keep writing and keep saying 5 and 6 and 7 and 8 and 9 and 10 and blah, blah, blah and blah, blah, blah. And I'm going to keep overwriting whatever happens to be found after the end of my buffer. What exactly am I going to be overwriting here? Well, I'm going to be writing potentially some other function arguments. Notice right here, these are gone, destroyed. And then what am I going to do? I'm going to keep writing and I'm going to keep overwriting the return address. And that's when the problems actually start happening. Overwriting that return address with an input of my choosing, of the attacker's choosing, basically allows me to trick that application into reading that return address and believing that the address found in there is the location in memory where it is supposed to continue execution from. So of course, I'm not going to be writing just 5, 6, 7, 8, 9, 10 in here. I'm going to be writing actual code, binary code in there, hidden under an unvalidated input field, in an attempt to trick this function that when it finishes execution and goes back here and read the return address, that return address is now going to be the return address of my choosing. I'm basically going to tell that application, go to this address right here, which is part of my buffer overflow, go to this address, which might be located some other place in my code, and start executing code from there. And there you go. At this location right here, we might have our own malicious code. So this is one way of doing stack overflows, by relying on the fact that the stack, if unvalidated, if unchecked, can be overwritten, and the return addresses can be overwritten as well. Well, now you might be thinking, okay, so I've managed to overwrite the return address with an arbitrary address, but what exactly is located at that address? How do I push my own malicious code to a specific address in order to trick my program into executing it? Well, it's also part of the buffer overflow process, because your buffer right here, if chosen correctly, can actually store a lot more data. It might be a buffer that stores, I don't know, an uploaded file from a user. It could store megabytes or tens of megabytes in size, right? So that buffer here can actually be huge, right? I can start writing data to it here as much as I need. Now, part of this huge data, I could also include a piece of malicious code. So the problem now becomes, what is the actual return address that I need to write in here in order for that return address to point to my malicious code? So the problem here is actually a bit more complicated, because there are mechanisms that don't allow us to predetermine where our data is going to be stored, at which address in a memory. So the attacker is supposed to do a bit of phishing here. How do they know where this malicious code is going to end up? Well, they don't exactly know, but they don't even really need to know. What they could be doing as part of the rest of the buffer before this malicious code is to fill it with blank operations. A blank operation in assembly language is called a NOP, a no operation, no instruction. It's basically an instruction that instructs the CPU to do nothing. So doing nothing means it did nothing and then went on to the next instruction, which is also a no instruction. Have a NOP in here, have a bunch of NOPs in here, and a lot of NOPs in here, until the execution goes through all of these NOPs in here, and finally reaches the malicious code. Why is this useful? Well, it's because now the return address doesn't really have to pinpoint exactly the location of the malicious code. It can pinpoint whatever it happens to hit inside of this huge set of NOP instructions. And by the way, this one here is called a NOP sled, because it makes the program execution slide through all of these instructions. It could be tens of thousands of them, it could be millions of them in there, until it reaches the malicious code. Of course, it's going to slide through them in a nanosecond, so it's not going to take any effort to do so. But this one allows the attacker to avoid the necessity of pinpointing the exact location of that malicious code as part of the buffer. It only needs to hit somewhere in between this huge NOP sled right here. That's it. This is the bullseye. This is where it needs to hit. This is where the return address is supposed to point. Anywhere in this location is okay, because at some point after going through all of these NOP instructions, it is going to hit the malicious code. So that's, in a nutshell, the simplest explanation I could muster about a stack overflow, which is a specific type of buffer overflow. I would strongly encourage you to view the videos about buffer overflows in my CySA Plus course, the cybersecurity analyst training, in which this situation is described in a bit more detail. So how do we mitigate this? Well, starting with input validation, but of course input validation is imperfect, because if we had perfect input validation, again, we wouldn't have anything else to talk about in this training. So let's think about some other methods. The use of safer functions and safer programming languages. Not all programming languages allow you to perform this type of copy operations with no boundary checking. Now, there are unsafe functions and there are safe functions. You should refer to the documentation of the programming language of your choice in order to determine which of these functions can be safely used or which of these functions can potentially cause a buffer overflow. Address space layout randomization. This is an operating system feature that allows programs to be randomly allocated all over the entire available memory, which kind of makes it a bit more difficult for an attacker to guess where their buffer overflow is going to end up in which memory location it's going to end up. A stack canary, it's a kind of a watch pointer that you can enable internally in an application for a specific return value of a function. So this is some sort of a warning mechanism to tell you whether that return value has changed, because you don't expect that return value to ever change once you have entered the actual function on the stack. All right, so that's some sort of a warning mechanism as to a potential buffer overflow that might be happening, a stack overflow that might be happening. And finally, we have data execution prevention. That's a security feature built into CPUs that don't allow applications to execute code from any location in the memory. So if we know that the code for an application is supposed to be found only within a specific area of the memory, we're only going to allow that application to execute code from there. We're not going to allow it to jump the execution and start executing instructions from a random location in the stack. A special type of overflow is called an integer overflow. Now, an integer is just a numerical value, which in programming languages can be unsigned or signed. That is, if it's signed, it can also hold negative values and positive values. As you probably know, all the data inside of a computer is represented in binary form, so it's just a bunch of zeros and ones. An 8-bit integer, it basically means that it can store 2 to the power of 8 numbers, right? So it's up to ranging from 0 to 255. 16-bit integers, 32-bit integers, 64-bit integers, and so on work exactly the same way. Now, as long as you don't run into negative numbers, integer overflows are going to behave just like the odometer on your car or on any counter you might have in your home. Whenever it reaches the maximum value, it's going to jump to 0. All right, that's a behavior of an integer overflow that doesn't support any signed values. So it's always positive. It's never in the negative. Now, this behavior, if unchecked, can cause, for example, a web store. If sufficient merchandise is added to the shopping cart and you reach a maximum that can be stored for the cost of that merchandise, you reach the maximum and then you add some more. After that maximum, you might end up with an amount of 0 or just a few dollars. It's simply because the buffer that was designed to store that value cannot store any more than its max. Now, a special type of this problem occurs whenever those integers are signed. So whenever the data structure that stores that numerical value can accept a negative value as well. Normally, negative values in binary are represented as a leading 1. Notice here that for number 1, okay, we have leading 7 zeros and then the binary 1 at the end. Now for -1, notice that the first bit here becomes the sign bit, right? So the first bit here, when it's set to 1, it becomes a indication that says this is actually a negative number. And of course, the rest of these digits here indicate the actual value. Now you can probably guess what's going to happen whenever this number right here reaches its maximum. That is this value, 127, okay? Remember, the first bit is the sign bit. So these are the valid integer values that we can assign. Now this right here, this is the value of 127 in binary. If I happen to add 1 to this value, it becomes a leading 1 with 7 trailing zeros, which in an unsigned world, it would mean 128. But in a signed world, it might mean something such as -0. It basically have a sign of minus here at the front, and then all the digits are 0. So if I keep adding digits in here, if I keep adding them, I'm going to go lower and lower in the negative values. So I have a -1 here, -2, and so on until I reach -127. And you can probably guess now, if I add 1 more to this, I'm going to end up with where I began, right? I'm going to end up with all zeros, which is a zero in both signed and unsigned interpretation. So this cycle here, going through positives and negatives and adding one to a high positive and ending up with a negative, this is a very bad situation if left unchecked. Remember, if we go back to the example of the shopping cart, right? Assume that at some point, the shopping cart can only hold as much as, I don't know, maybe $2 billion or something like that. And you add one more product in there, and this entire number here jumps from its maximum to a negative value. And you suddenly need to pay minus $5 for a shopping cart of 2 billion. Okay. Now that's probably an order that is not going to go unnoticed. But nevertheless, this is one of those flaws that can be found in a lot of programming languages simply because nobody thought about the fact that somebody might actually cause that buffer to go as high as its maximum. Normally, we're running today with 32-bit integers, which if they're signed, it means that we actually can use 31 bits, which allows us to allocate about 2 billion values. In most cases, that's enough, right? If we're counting things in an application, if we're counting users, if we're counting actions, if we're counting ammo in a game or enemies or whatever, it's probably enough. But what if somebody hacks that application and suddenly makes that number jump higher than its maximum? Then some abnormal situations such as these can happen. Again, this can be mitigated using input validation, but you have to be careful about this. Be careful from the very beginning when you design your application, what type of data structures you're using and what type of value do you expect to receive in those data structures. Another type of an attack, or more likely an error that can happen and can also be translated as an attack, is called null pointer dereferencing. Now let's divide this by words, starting with a pointer. Now a pointer is just a memory address where some data is stored. It's often used in pretty much any programming language out there in order to send that code execution to read or to write a value stored in memory at a specific address. That's a pointer. It's a pointer to that address. And when you attempt to do something at that address through that pointer, whenever you attempt to read that value or to change that value, this is called pointer dereferencing. So we're basically translating that pointer into its actual contents, and then we start working with the contents of that address. That's pointer dereferencing. What about null pointer dereferencing? Well, trying to access or to modify the contents of a pointer that wasn't initialized. And an uninitialized pointer means that it's pointing to a zero memory location, the memory location of zero. That's an illegal operation in programs and in operating system. You're not allowed to write and to read data from that zero memory location. So that's a null pointer. Null pointer is the pointer that hasn't been initialized and is still pointing to zero. If you attempt to do this, the program will most likely crash. Now, a null pointer can happen due to normal programming error. A programmer just forgot to initialize that pointer. It can also happen due to an integer overflow, which was supposed to point to a location that is now actually part of an overflow process and it's now zero. It can also happen due to a buffer overflow or to a stack overflow when the specific memory location was now uninitialized or that pointer was overwritten and it's now pointing to the wrong location. Quote unquote, fortunately, I would say that this type of error, this type of an attack can only have one end result. That is the crash of an application, which might be enough if the purpose is to cause a denial of service. This could also be a potential malicious intent. Another programming error, common programming error, is called a race condition. Now, race condition happens whenever a program that is made up of multiple processes or multiple execution threads or can process data from multiple sources at the same time doesn't allow you to strictly determine the order of the operations and in which order they will happen. And this is very important because with computers, we expect everything to be completely deterministic. We want to know the exact order in which the code is going to be executed, because if it's something, it's a gray area in there. If we don't know how that code is going to be executed, it's next to impossible to figure out if there's a vulnerability in there, if there's a potential for an exploit, right? We have to be able to track the exact program execution. And not only because we need to track for exploits, but also because we need to be able to ensure that we never end up in situations where data integrity might be compromised. Let me give you an example of this, of a race condition. And that one is called time of check, time of use. All right, so let's assume that we have a bank account, and this is the timeline right here. And this bank account starts with $100 in its bank account. Okay, everything okay so far. Now let's assume that we have a user A, and that user connects to an ATM and then wants to query the amount in that bank account. What's that user going to see? Well, that user is going to see, of course, the $100 in that account. There we go. Now let's assume that it's pretty much at the same time or before user A has a chance to do anything about that query, another user comes in, user B. And that user performs a query as well. And what is that user going to see? Well, it's still going to see the same $100 in the bank account. Nobody has withdrawn them just yet. So what happens now if user B is just a bit faster and decides to withdraw those $100 before user A? So user B now performs a withdrawal. So now user B has $100 in its hand, and the bank has 0. And let's assume now that user A, as lazy as he is, has suddenly decided, after looking for a couple of minutes at the ATM screen, to withdraw those $100 as well, because what he saw was that the ATM does have $100, right? So he decides to withdraw them. Well, what's going to happen now? Without time of check, time of use integrity, the bank account is now going to hold minus $100, and of course user A is also going to have $100 in his pocket. Is this what we intended to do? Probably not. So what exactly is this time of check, time of use exception? The idea here is that whenever you're checking for a resource and then you decide to act upon that resource, these two operations here, operation 1 and operation 2, should actually be one single atomic operation. So they should be executed together or not at all. That's the definition of an atomic operation. Otherwise, we risk running into situations where two entities, two threads perhaps, check for a resource. They both believe it is available, but the first one that manages to act upon that resource makes it unavailable, which for a bank account might sound funny or even profitable, but for resources like disk access or putting locks on files or modifying the contents of a file on the disk or updating the cache or invalidating a cache, this can run into extremely dangerous situations, which in turn can be exploited by attacks destined to exploit this exact type of vulnerability. So normally your code should never allow situations such as these. Whenever you're trying to check for a resource, make sure you lock that resource until the moment where you are absolutely certain that you don't need it anymore, and then you release the lock so that nobody else is going to come in and put a lock on that resource or try changing that resource before you're done with it. And one way of exploiting this type of vulnerability is by having the actual attacker intervene in such a time of check, time of use exception. That is, an application perhaps writes some temporary data to a file, to a cached file, and then the attacker comes in, and before the application can actually get to read that file and reuse it, the attacker can change the contents of that file. So even if the application thought that it has just written some temporary data on the disk for future use, well, that data now has been altered, has been changed by the attacker, and the application has no way of knowing about this, of course. Memory leaks are another type of software flaw that is extremely widespread and can be found in pretty much any software out there. Now, a memory leak, by definition, is when a process uses a certain amount of memory, is done with that region of memory, and then forgets to free it up to make it available again for the system and for other applications, or even for the same application for future use. If this happens over time, more and more and more, especially this is especially bad with background services and server applications that run over a time span of days, weeks, months, sometimes even years. If there's a small memory leak, continuously happening in there, basically the amount of free memory gets smaller and smaller and smaller over time until the system runs out of memory, which in turn is going to cause a system crash. And of course, all the applications on that system are going to crash as well. This can be accidental. In many situations, it's actually accidental due to the programmers that forget to free up the memory that is no longer in use, but it can also be malicious. And it's not necessarily that the memory leak is intentional with a malicious purpose. So it's not necessary that the end result, the end purpose of an attacker is to cause a system crash, but it can happen due to badly written malware. So don't assume that malware doesn't have bugs. Of course it does, right? And it might even have vulnerabilities. And one of them might be a memory leak. So even though the attacker has managed to cover its traces and perhaps replace some operating system files with their own, well, those files might not be working so well as the original operating system files. And you might end up seeing that, well, up until now, everything was working fine. But since an operating system file was changed, you run out of memory every 2 days on a server. That's because there's malware running in there that is accidentally eating up the memory of your entire system. DLL injection is another type of potential software risk that your applications might be exposed to. Now, a DLL, Dynamic Link Library, is not necessarily called a DLL. We just call them DLL because we've gotten used to the DLL extension in Windows. But in other operating systems, they have other extensions and they work pretty much the same. They're just pieces of compiled code as external files that can be loaded into your main application whenever you need some additional functionality. You're going to find DLL files you're going to find them with drivers, right? Whenever a driver needs to be loaded, it actually loads some DLL files. Whenever an application needs to load a plugin, a skin, or an additional plugin for, let's say, an archival utility in order to be able to open up a more exotic type of archive, that's going to be probably a plugin that gets loaded dynamically at runtime under a form of a DLL. So it's pre-compiled binary code which can be executed just like your normal application code. It's just that it gets loaded whenever it is needed. Now, as you can probably guess, these DLL files can be maliciously altered as well. So they can be loaded into your main application, and the application is going to execute the code within those files blindly without knowing whether it's malicious or not. There are several ways in which DLL injection can be performed. A traditional method would be to simply replace one of the application's DLL files with a malicious one, or you can dynamically attach the process as it is running. There are many ways in which this can be performed, but most of them require some sort of higher level privileges in order to be conducted. Sometimes applications load DLL files for additional functionalities such as loading security agents or additional monitoring functionality, or to provide compatibility with legacy systems. If you ever try to run an executable file into a compatibility mode for Windows XP, for example, or an older release or Windows 7, well, what happens in the background is that a code library gets dynamically attached or injected into that main application that allows the system calls and every interaction between that application and the operating system to match those system calls that were available back in a previous version of Windows. And that piece of code is called a shim in Windows. And it's also the type of dynamic library that gets loaded at runtime. Finally, one last example here, because we do need to stop with this video at some point. One last example of a vulnerability that can be exploited once a host is compromised. It's called the pass the hash. Now, the pass the hash attack has been traditionally associated with Windows systems starting with the NT versions long time ago. But as a general type of attack, it relies on the ability of an attacker that has already compromised the host to extract any password hashes that are stored locally on the machine, especially if that machine is already authenticated into a single sign-on system. Now, with single sign-on, you probably know that we're not exactly sending the password on each and every conversation that we're having with all these systems enabled for single sign-on, but what we're actually sending is a temporary token that is generated for us, and that token allows us access to multiple services. Now, that token is also stored locally somewhere on the machine, because that's why your machine doesn't ask you for your credentials, because it already knows what token to present whenever it's accessing one of those SSO enabled systems. Well, those tokens can be stored locally, and sometimes they can be stolen, compromised whenever that machine is compromised entirely. And passing the hash is an attack that relies on extracting that hashed password from the database of the local system, and then attempting to use the same hash to impersonate that user into another system. So basically, it's a type of privilege escalation, if you wish, or lateral movement when you're using the current authenticated state of that user to impersonate and present it to a different system to be authenticated. So as we said, this attack was traditionally associated with the legacy Windows systems, those relying on NTLM authentication. Now, unfortunately, even though modern Windows systems don't allow this vulnerability to happen anymore, unfortunately, some admins still enable backwards compatibility, perhaps because they don't know what it's about, or perhaps because they actually attempt to provide network access or single sign-on services to legacy systems that are still running, let's say, Windows 7 perhaps, or even older Windows versions. Just by enabling this backwards compatibility, unfortunately, opens up even recent Windows versions to a vulnerability called pass the hash, where those credentials are stored locally in the cache and they can be easily extracted by an attacker who has managed to compromise that host. Actually, it doesn't even have to compromise the host entirely. It only needs to compromise an application that is running on the host, and if that application has access to that database on the disk, then it's enough. Wow, I need a break. So that's it about application security and software development security. I'm gonna talk a bit more about this in the following videos, but I try to simplify it as much as possible. If you want to know more about this, check out my series on CySA Plus, on Cybersecurity Analyst Plus, also from CompTIA. All of these are explained in much more detail in there. But for now, this should be enough for your studies, for your exam, for your peace of mind. So like, subscribe, comment, and support this channel if you can. See you on the next video. Thank you and bye-bye.